Well, you had a little time to get started. Okay, so I'm going to begin. I'm hoping you got your document in front of you. You got your phones away. You got your attention on me. You got a writing utensil, and we're ready to roll. So we're going to talk a little bit more about gravitational fields here. The Earth pulls on the moon. Here's the Earth. I'll use a tennis ball as the moon, right? And we know already that the Earth pulls on the moon. But is there anything connecting them? No. There is not. Like if I just put my moon model down, can I pull on it? Can I? Really? If like all I have to do is want to and I can do it? Really? Well, I don't know. Anything is possible? I really want. You don't know how bad I want to do this because it would be very cool. Or if I had Jedi powers and I could just like.
Okay, first of all, who doesn't want those powers?
Well, yeah. So I don't think. No, I disagree. Anything is not possible. I cannot apply force to that moon without touching it. Okay, but yet the Earth pulls on the moon and there is no contact. We regard this as action at a distance. This idea of action at a distance. So what is going on here? Okay, and it's because the Earth and Moon interact with each other even though they are not in contact. Now we can look at this in a different way. We can regard the Moon as interacting with the gravitational field of the Earth. You guys realize I'm teaching here, right? Laying foundation for later. When there's questions, you gotta listen so you understand. That's your role in this. I do the talking, I do the explaining, you do the listening. Two-way street. We looked at this in a different way. We regard the moon as interacting with the gravitational field of the Earth. So what does that mean? Well, the Earth, as every mass, every object has this gravitational field. So we can draw that on there, right? And now you see that the little rocket here is touching what? It's touching the field lines. It's touching the Earth's gravitational field. There is contact with this gravitational field. Are we currently in the Earth's gravitational field? Yeah. We are. Can you feel it? Can you see it? Does it exist? Well, yes and no. No, it doesn't physically exist. Like you can't see it or touch it or smell it or anything like that. But it's a model of what's happening. Josh, you're not listening, man. You're talking about something else with your hands. Here's where you learn. You gotta listen. Okay? So there is this contact. We use this concept of the field to explain, to model why there is no contact. And we call this action at a distance. Okay? The properties of the space surrounding any mass can be considered to be altered in such a way that another mass introduced to this region will experience a force. This alteration of space is the gravitational field. Now, it's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the mass of the Earth and other planets or stars that are the sources of these fields. The field concept plays an in-between role in our thinking about the forces between different masses. So it's a way to explain what's going on. It's part of the gravitational theory. And you remember the word theory. What does the word theory mean? It's a way to explain. It's a way to explain. Will theories ever be proven? They will never be proven. Theories do not become laws. Theories are explanations, and there are robust theories and there are speculative theories. And robust theories have a lot of evidence. All right. A gravitational field is an example of a force field. For something in the space experiences a force due to the field. Another force field you may be familiar with is a magnetic field. You've probably seen iron filings lined up in patterns around a magnet. You probably saw that in about grade 5 or 6 or something, right? Yeah. No? Some of you maybe missed that day. Here's a picture right here. The pattern of the filing shows the strength and the direction of the magnetic field at different points in the space around the magnet. Where the filings are closest together, the field is strongest. Why did I say it like that? Where the filings are closest together, the field is the strongest. And the direction of the filing shows the direction of the field at each point. Where are these filings closest together on this picture? These areas right here, which are known as the poles. The magnetic poles, right, Adam? Okay, question for you. Is there such a thing? Does the Earth have a gravitational field?
Yeah.
Is there such a thing as a gravitational pole?
Yeah. No. Yeah, I'd say. Yeah. North and south gravitational.
Is there such a thing as a gravitational pole?
Yeah.
Why do you say yes, Adam?
Because the gravity comes from a certain spot.
Okay.
I want to say it's like a monopole.
Oh, Jared used a big word. A monopole. What does that mean, Jared?
It's like a magnet. A magnet has two poles on each side, and a monopole is just one pole.
One pole. Do magnets have monopoles?
No.
Or can, sorry, let me rephrase. Can magnets have monopoles?
Yes.
They do exist, they're kind of mind-blowing.
Yeah.
So, okay, so I said this morning, the Earth does not have a gravitational pole. But I'm hearing what Jared's saying. He's saying, I think this is what he's saying, and you correct me if I'm wrong, but I think what he's saying is, if I extend these gravitational lines all the way towards the center, well, they would end up at one point, which Jared is calling the... I think we should call this Jared's theory. Did you say that? The Hogan-McQueen theory. I have never considered that before in all these years. Wow, that's awesome. Yeah? I apologize. I didn't. Okay. The pattern. Awesome, you guys. Let's move on. The pattern of the Earth's gravitational field can be represented by field lines. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. Yay, I see lots of people got the cue. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. At each point on a field line, the direction of the field at that point is along the line. Arrows show the field direction. A particle, astronaut, spaceship, or any mass in the vicinity of the Earth will be accelerated in the direction of the field line at that location. And the strength of the Earth's gravitational field, like the strength of its force on objects, follows the inverse square law, which I'm going to talk about right away. It is strongest near the Earth's surface and weakens with increasing distance from the Earth. And so, this picture over here on the left, now somehow I've lost some lines, some arrows, but you guys have them all, I think, right? Okay, so what I want you to do is I want you to extend them out, like this. Okay? And tell me, where is it the weakest? Out here, far away. And where is it strongest? At the Earth's surface, right? And Jared's saying that those are going to continue towards that monopole. Okay, now what does this inverse square law mean? Now, interestingly enough, I was just talking about this concept with grade 12s too. Okay, so here's how the inverse square works. If you're 2 times as far away, okay, your strength, your gravitational field strength, TH, is 1/4. How the heck did I get 1/4? Inverse square. Where do I get 1/4 from? Inverse means 1 over 2, but not 2, 2 squared, which is 1 over 4. Pardon me? No, it's called the inverse square. If you're 3 times as far, then your field strength is going to be 1 over 3 squared, or 1/9. If you're 4 times as far, you're going to be 1 over 4 squared, 1/16. Excuse me a second. Make sense? That whole inverse square law thing? Okay, now that's an important concept. This is probably your first time you've seen it, but it's true for gravity, gravitational fields, magnetic fields, sound, light, just about anything that sort of expands in sort of 3 dimensions. Okay? So if we turn the basement light on over here, for example, well, it kind of looks like someone's basement, right? The ground's basement, right? So Rachel will say is, I don't know, we'll say she's 2 meters away. Okay? And if I go here, 4 meters away. I'm twice as far, so the light here is actually 1/4 the brightness. Like if I stand here and look at the light, and I go here, it's actually 4 times brighter, right here. And if I go 2 more, if I now 3 times, anyone, yeah. If you go 3 times as far, it's now 1/9 as bright. It's 9 times brighter where she is than it is here. Same is true for sound. If you're, 2 meters away from a big giant speaker at a rock concert, and I'm 6 meters away, it's going to be 9 times louder where you are. Don't stand next to speakers. Give me a headache. Okay, now, the classic question. Have you ever wondered what would happen if you dug a hole all the way through and you jump in? Yeah, the common myth is you're going to end up in China.
No, you're going to end up in the center of your...
Are you? Okay, well, forget about lava and hot temperatures and, not having a lunch and stuff like that. What would happen? Well, A, you're not going to end up in China, by the way, because China's in the northern hemisphere and so are we. So you would actually end up about, there's Lake Manto right where my finger is, so it's going to be like about...
If you're lucky, Madagascar.
Didn't you just kind of bounce back and forth on the side?
Out there. Just off the coast of Antarctica. Yeah, you got lucky, you might got lucky. 9 times out of 10, you're going to hit water. But anyways, let's talk about how will this motion happen. Okay, so does the gravitational field exist inside the Earth as well?
Yes.
Yes. I mean, if you dig a little hole that's only a couple inches deep, you stand in it, there's still gravity, right? You go a foot deep, still gravity, right? Still gravity everywhere you go, right? So the gravitational field of the Earth exists inside the Earth as well as outside. To investigate the field beneath the surface, imagine a hole drilled completely through the Earth, say from the North Pole to the South Pole. Okay? Forget about impracticalities such as lava, high temperatures, not having a lunch. Consider the kind of motion you would undergo if you fell into such hole. What say you, Anna? You would not. Here's what would happen. Okay? If you started at the North Pole end, you'd fall and gain speed all the way down to the center. So I'm just going to draw a little person here. Okay, and you'd have to ignore air resistance, right? So you would continue to speed up and speed up and speed up. And when you got to the center, you would actually be going the fastest you could go, right? You would continue to fall faster and faster and faster and faster. Nope. Then you would start slowing down as you went away. And let me tell you, you would go exactly to right there. And some poor little penguin out for a walk in the Antarctic, suddenly Lawson would pop up in this hole, and he would be upside down. Wouldn't he, right? He jumped in feet first, right? He'd pop out the other side, and Lawson would pop up, and the penguin would be looking at his feet. And then what would happen? He'd go right back down again in the hole, right? And then a little while later, he'd pop out at his workshop, face like head up kind of thing, right? And he would go back and forth. Why would you stop? What's stopping you? Oh, well, if you wanted to stop, good. Yeah. Yeah.
Wouldn't it attract you to the size of the hole because it would be pulling you towards
She's saying that as you're I like this. You're falling down. You've got a half an Earth on one side of you.
Yeah.
You got another half. Oh, so wouldn't it pull you this way the same amount that it pulls you this way and keep you in the center? Right? The same thing front and back, anyway, right? It's a thought. Yeah. Okay. Oh yeah, Josh and then Adam.
What you said, like you speed from falling down in the middle to get you be enough to get you right to the other side.
Yeah.
When you have to switch to the ground level.
You would have to assume that the Earth is perfectly sphere, which is not true.
Yeah, but if you came right to a hole and came up and landed on
Yes, absolutely. You would have to assume that the Earth is perfectly spherical, which it's not. In fact, wider at the equator. You know how like if you spin something or other, it sort of gets like inertia makes it, right? So it actually is like kind of fatter, I guess if you will, at the equator and sort of more squat. I think it's kind of mushed in at the pole. So you're right. Adam, you got something?
Wouldn't it be like when you like let go of something like a ball, whatever, like slow it down a bit?
Yeah.
Wouldn't that be the same thing?
Absolutely. You would lose. I mean, you would reach terminal velocity in about a minute.
Yeah.
And you wouldn't make it anywhere close to it. So, yeah. And you're right. A pendulum goes like this and loses because of friction and everything, right? So we're making a lot of crazy assumptions.
So,
Eventually,
someone actually managed to, like, I don't.
This is not an actual experiment.
I know, but if someone ever managed to do this, wouldn't there be like really big consequences on the Earth?
Yeah.
Well, you wouldn't want to walk too close to it.
Well, they already tried it.
Yeah, you know why? Because if you were to drill down, right, and you went all the way through, we already agreed there's a good chance you're going to end up, look at how much water there is, you're likely to end up in water. Where would that water go? You go flying towards the center, back up to the other side, but would it just sort of go pop and stop there and then go back?
Yeah.
No, because there's like a gazillion liters of water coming back, right? So, yeah, but that's because Lawson's only this tall. There's nothing pushing them, right? If it was water, there'd be all that water coming back as well. You'd have this great big. That'd be cool. We should try that. Well, we wouldn't have to worry about exams. Yeah. Go ahead, Ross. Go ahead. Okay. Rasmus's question is this. I usually have to bring this one up myself, so I'm glad you asked. If you were to dig that hole and then build a ladder and then walk all the way down and you got to right to the center, and then you were to jump off the ladder and you're right at the center, what would happen? You would float. Because you're at Jared's monopole, right? Gravity all around would be equal. Guys are right on top of things. Okay, let me carry on here. I got to get going. You should know you'd gain speed moving toward the center. You'd lose speed moving away from center. Without air drag, the one-way trip would take nearly 45 minutes to get there. 45 minutes there, 45 minutes back. Interestingly enough, that's about how long it takes for a satellite to orbit the Earth as well. About 90 minutes to go all the way around. It's actually, and it's because of gravity. It's the same process. If you fail to grab the edge, you'd fall back towards center, overshoot, and return to the North Pole at the same time. Okay, now, pay a little attention here because there's a few little wrinkles. Repeat this trip with an accelerometer of some kind. Your acceleration at the beginning of the fall is g, 9.8, but you find it progressively less as you continue toward the center of the Earth. Why? Why would the gravity become less? Don't read ahead. Why would the gravity down, like a third of the way down, be less than 9.8? It's not an easy question. What's causing us to be pulled down? The big mass of the Earth, right? But if you're a third of the way down,
There's less mass underneath.
there's less mass underneath you, and in fact, not only that, Josh, but there's also some mass above you. So you are actually attracted above. So in fact, the gravity would not maintain a constant minus 9.8. It would change. The acceleration would change. Anybody remember what that's called when the acceleration changes?
Deceleration.
Such a jerk. No, it's called the jerk factor. It's called the jerk. When the acceleration changes, it's called jerk. That's what Mr. Ray said, that I was a jerk? Say that? Yes, Raston.
So the 9.8 is reference to how big the Earth is below mass.
The 9.8 is because of the Earth's mass. If the Earth was bigger, we'd have on the moon is 1/6, so gravity there is only 1.6. It's solely dependent upon the mass of the Earth. Jay, you should put that away and you should listen. You tell your mom you're in physics and you really have to listen.
doesn't the moon like get really close to the Earth?
Because it's also doing what?
Technically, it's going farther away.
Well, it does not, it's not a perfect circle either, right? But it's moving sideways. Moving sideways and falling at the same time. Yeah, it's like free fall. Yeah. Okay, I gotta move on. Repeat this trip with an accelerometer of some kind. Your acceleration at the beginning of the fall is g. You'd find it progressively less as you continue toward the center of the Earth. Why? Because as you're being pulled downward toward the Earth's center, you're also being pulled upward by the part of the Earth that is above you. In fact, when you get to the center of the Earth, the pull down is balanced by the pull up. You are pulled in every direction equally, so the net force on you is 0, right in the center, the monopole. There is no acceleration as you whiz with maximum speed past the center of the Earth. The gravitational field of the Earth at its center is 0. And so, in fact, maybe Adam's idea about it being the strongest there, well, maybe that's not entirely true, because actually the gravity is 0. Oh, now it's not true.
Well, I don't know what you're talking about.
The whole monopole thing. They are, I mean, they get stronger as they get closer, right? But because it's equally balanced out, so it's, yeah, I don't know. I'm going to have to think about that one. Deep thoughts, yes. Okay, now, oddly enough, I'm not going to bother with that, because we've had lots of good questions. Quick question here. I'm not going to bother with clickers. We've got to move on. There's only 2 of them. If you stepped into a hole through the center of the Earth and made no attempt to grab the edges at either end, what kind of motion would you experience? If you jumped into the hole, what kind of motion would you experience? Would you fall all the way through at a constant speed and stop when you reach the other side? Would you fall all the way through, speeding up the entire time, and stop when you reach the other side? Would you oscillate back and forth? That's what oscillate means, to go back and forth, with a changing speed, which is called simple harmonic motion? Or would you oscillate back and forth with a constant speed? C? You are right. C, changing speed. Good little practice on multiple choice questions. Halfway to the center of the Earth, would you weigh more or weigh less than you weigh at the surface? Oh, you should have grabbed it this one. Halfway to the center of the Earth, would you weigh more or would you weigh less? Oh, I got some saying more, I got some saying less. Remember, when you're halfway to the center, you've got some Earth above you. You would weigh less because the part of the Earth's mass that pulls you down is counteracted by the mass that is above you. Pardon me? They're balanced, exactly. Okay. Okay. Yesterday we talked a little bit about weight and weightlessness. I'm gonna let you read that on your own if you want. I'm gonna give you the quick version of it. I gave you the quick version yesterday. I'm looking at the clock. I want to make sure you get some time to work. Let's just quickly. This is basically what I talked about yesterday. Let's just kind of look at the cartoon thing here, right? This one here. How can you tell from the picture? Is this elevator accelerating, traveling at a constant speed, or slowing down? It is constant. It's either not moving or it's at a constant speed. You should draw that in there. And you'll notice that they are, the person with the weird hair is normal weight. But this one here, what is this one doing? How do you know? There is an arrow going up, and there's these sort of little smoke things down here, right? So it's going up, and it's accelerating up, and the person has a greater weight. So that's just a visual from yesterday, right? What if you are accelerating down? Here's the little smoke puffy things. You weigh less, right? And what if it breaks? You have no weight at all, right? You are apparent weightless.
So you're in a state of free fall.
You are in a state of free fall for, as long as the elevator shaft is long, I guess, right? I'm going to let you read that on your own. I don't think there's anything in there that's of importance. Okay. I'm going to stop.